The logical universe. Calculus underwent a metamorphosis in the second half of the 17th century. It became so systematic, so penetrating, and so powerful that many historians say calculus was invented then. According to this view, before Newton and Leibniz, there was proto-calculus, afterwards calculus. I wouldn't put it that way myself. To me, it's been calculus along, even since Archimedes harnessed infinity. Whatever it's called, calculus transformed dramatically between 1664 and 1676, and it changed the world along with it. In science, it allowed humanity to start reading the book of nature that Galileo had dreamed of. In technology, it launched the Industrial Revolution and the Information Age. In the philosophy and politics, it left its mark on modern conceptions of human rights, society, and laws. I wouldn't say calculus was invented in the late 17th century. Rather, I would describe what happened as an evolutionary breakthrough analogous to a pivotal event in biological evolution. In the early days of life, organisms were relatively simple. There were single-cell creators, something like the bacteria of today. That era of unicellular life continued for about 3.5 billion years, dominating most of the Earth's history. But around half a billion years ago, an astonishing diversity of multicellular life burst forth in what biologists call Cambrian explosion. In just a few tens of millions of years, an evolutionary split second, many of the major animal phyla suddenly emerged. Similarly, calculus was the Cambrian explosion for mathematics. Once it arrived, an amazing diversity of mathematical fields began to evolve. Their lineage is visible in their calculus-based names in adjectives like differential and integral and analytic, as in differential geometry, integral calculus, and analytic number theory. These advanced branches of mathematics are like the many branches and specified species of multicellular life. In this analogy, the microbes of mathematics are the earliest topics, numbers, shapes, and word problems. Like unicellular organisms, they dominated the mathematical scene for most of its history. But after the Cambrian explosion of calculus 350 years ago, new mathematical life forms began to proliferate and flourish, and they altered the landscape around them. Much of the story of life is a tale of progress toward greater sophistication and complexity, building on earlier precursors. That's true of calculus as well. But what is the story of build? But what is the story building toward? Is there any direction to the evolution of calculus, or is it, as some would say, of biological evolution, undirected and random? Within pure mathematics, the evolution of calculus has been a story of crossbreeding and its benefits. Other parts of math were invigorated after they were crossed with calculus. For example, the ancient study of numbers and their patterns were revitalized by an infusion of calculus-based tools like integrals, infinite sums, and power series. The resulting hybrid fields the resulting hybrid field is called analytic number theory. Likewise, differential geometry used calculus to shed light on the structure of smooth surfaces and reveal cosines they never knew they had unimaginable curved shapes in 4 dimensions and beyond. In this way, the Cambrian explosion of calculus made mathematics more abstract and more powerful. It also made it more like a family. Calculus exposed a web of hidden relationships tying all parts of mathematics together. In applied mathematics, the evolution of calculus has been a story of our expanding understanding of change. As we have seen, calculus began with the study of course, where the changes were change in direction, and it continued with the study of motion, where the changes become changes in position. In the aftermath of its Cambrian explosion, and especially with the rise of differential equations, calculus moved on to the study of change much more generally. Today, differential equations help us predict how epidemics will spread, where a hurricane will hit land, and how much to pay for an option to buy a stock in the future. In every field of human endeavor, differential equations have emerged as a common framework for describing how things change around us and inside us, from the subatomic domain to the farthest reaches of the cosmos. The logic of nature. The earliest triumph of differential calculus, of differential equations, altered the course of Western culture. In 1687, Isaac Newton proposed a system of the world that demonstrated the power of reason and ushered in the Enlightenment. He discovered a small set of equations, his law of motion and gravity, that could explain that mysterious pattern Galileo and Kepler had found in falling bodies on Earth and planetary orbits in the solar system. In so doing, he erased the distinction between the earthly and celestial realms. After Newton, there was just one universe, with the same laws applying everywhere and always. In his magisterial three-volume masterpiece, Mathematical Principles of Natural Philosophy, often known as the Principia, Newton applied his theories to much more: the shape of the earth, with its slightly bulging waistline by the centrifugal force of its spin, the rhythm of the tides, the eccentric orbits of comets, and the motion of the moon, a problem so difficult that Newton complained to his friend Edmund Halley that it had made his headache and kept him and made his head ache and kept him awake so often that he would think of it no more. Today, when college students study physics, they are taught classical mechanics first, the mechanics of Newton and his successors, after which they are told that it has been superseded by Einstein's relativity theory and the quantum theory of Planck, Einstein, Bohr, Schrödinger, Heisenberg, and Dirac. There's certainly a lot of truth to that. The new theories overturn of Newtonian conceptions of space and time, mass and energy, and determinism itself, replacing it in the case of quantum theory with a more probabilistic statistical description of nature. But what has not changed is the role of calculus. In relativity, as in quantum mechanics, the laws of nature are still written in the language of calculus, with sentences in the form of differential equations. That, to me, is Newton's greatest legacy. He showed that nature is logical. Cause and effect in the natural world behave much like a proof in geometry, with one truth following from another by logic, except that what is following is one event from another in the world, not one idea from another in our minds. This uncanny connection between nature and mathematics harks back to the Pythagorean dream. The link between musical harmony and numbers discovered by the Pythagoreans led them to proclaim that all is number. There were two something. Numbers are important to the working of the universe. Shapes are important too. In the book of nature that Galileo dreamed of, the words were geometrical features. But as important as numbers and shapes might be, they're not the two drivers of the play. In the drama of universe, shapes and numbers are like actors. They are quietly directed by an unseen presence, the logic of differential equations. Newton was the first to tap into this logic of the universe and build a system around it. It was not possible before him because the necessary concept hadn't been born yet. Archimedes did not know about differential equations. Neither did Galileo, Kepler, Descartes, or Fermat. Leibniz did, but he was not as inclined toward science as Newton or nearly as virtuosic mathematically. The secret logic of the universe was vouchsafed to Newton alone. The centerpiece of his theory is his differential equation of motion. It ranks as one of the most consequential equations in history. It says that the force F on a moving body is equal to the body's mass m times its acceleration a. It's a differential equation because acceleration is a derivative, the rate of change of the body velocity, or in Leibnizian terms, the ratio of two differentials. Here, dv is the infinitesimal change in the body velocity v during an infinitesimal time interval t. So, if we know the force body F on the body, and if we know its mass m, we can use F equal ma to find its acceleration via a equals F over m. That acceleration in turn determines how the body will move. It tell it tells us how the body velocity will change in that next instant, and its velocity tells us how its position will change. It, in this way, F equals ma is an oracle. It predicts the body's future behavior one tiny step at a time. Consider the simplest bleakest situation imaginable: an isolated body alone in an empty universe. How will it move? How will it move? Well, since there's nothing around to push or to pull it, the force of the body is zero. F equals zero. Then, since m is not zero, assuming the body has some mass, Newton's law yield F over m equals a equals zero, which implies that dv over dt equals zero as well. But dv equals dt equals zero means the lump body velocity does not change during the infinitesimal time interval t, nor does it change during the next interval or the one after that. The upshot is that when equals zero, uh, a body maintains its velocity forever. This is Galileo's principle of inertia. In the absence of an outside force, a body at rest stays at the body at rest stays at rest, and a body in motion stays in motion and over a constant velocity. Its speed and direction never change. We have we have just deduced the law of inertia as a logic consequence of Newton's deeper law of motion. F equals ma. Newton seemed to have understood early on, back in his college days, that acceleration was proportional to force. He knew from studying Galileo that if there was no force on the body, it would either stay at rest or continue moving in a straight line at a constant speed. Force, he realized, was not needed to produce motion, it was needed to produce changes in motion. It was force that was responsible for making bodies speed up, slow down, or depart from a straight path. This insight was a big advance over earlier Aristotelian thinking. Aristotle didn't appreciate inertia. He imagined that a force was needed a to keep a body moving. And to be fair, that's true in situations dominated by friction. If you are trying to slide a desk across the floor, you have to keep pushing it. Once you stop pushing, the desk stops moving. But friction is much less relevant for planets gliding through space or apples dropping to the ground. In those cases, the force of friction is negligible. It can be ignored without losing the essence of phenomenon. In Newton, in Newton's picture of universe, the dominant force is gravity, not friction, which is as it should be given that Newton and gravity are so closely associated in the popular mind. When most people think of Newton, they immediately recall what they learned as a children, that Newton discovered gravity when an apple fell on his head. Spoiler alert, that's not what happened. Newton did, didn't discover gravity. People already knew that heavy things fell, but nobody knew how far gravity went. Did A then at the sky? Newton had a hunch that gravity might extend to the moon and possibly beyond. His idea was that the moon's orbit was a kind of never-ending fall to the earth, but unlikely a falling apple. A falling moon does not crash to the ground because it's also simultaneously creasing sideways due to inertia. It's like one of Galileo's cannonballs gliding sideways and falling at the same time, tracing a curved path, except that it's gliding so fast that it never reaches the surface of the spherical Earth, curving away beneath it. As its orbit deviates from a straight line, the moon accelerates, not in the sense that its speed changes, but its direction of motion changes. What pulls what pulls it off a straight line path is the incessant tug of the Earth's gravity. The resulting type of acceleration is called centripetal acceleration, a tendency to be pulled toward the center, in this case the center of the Earth. Newton inferred from Kepler's third law that the force of gravity weakened by distance, which explained why the more distant planets took longer to go around the Sun. His calculation suggested that if the Sun was pulling on the planets with the same kind of force that drew an apple to the Earth and that kept the Moon in its orbit, that force had to weaken inversely with the square of the distance. So, if the separation between Earth and the Moon could somehow be doubled, the gravitational force between them would weaken by a factor of 4, 2 squared root 2. If the separation was tripled, the force would decrease by ninefold, not threefold. Admittedly, there were some dubious assumptions built into Newton's calculations, particularly the assumption of the gravity acted instantaneously at a distance, and if the vastness of space were irrelevant. He had no idea how this could be possible, but still the inverse square law intrigued him. To test it quantitatively, he estimated the centripetal acceleration of the Moon as it cycled the Earth at its known distance, about 60 miles, the radius of the Earth, and its known period of revolution, about 27 days. Then he compared the Moon's acceleration to the acceleration of falling bodies on Earth, which Galileo had measured in his inclined plane experiments. Newton found that the two accelerations differed by a factor encouragingly close to 3,600, which equals 60 squared. That was just what his inverse square law predicted. After all, the Moon was about 60 times farther from the center of the Earth than an apple falling from a tree on the Earth's surface, so its acceleration should be about 60 square times less. In later years, Newton recalled that he compared the force requisite to keep the moon on her orbit with the force of gravity at the surface of the Earth and found them answer pretty nearly. The notion that the tug of gravity might extend to the moon was a wild idea at the time. Remember that in Aristotelian doctrine, everything below the moon was held to be corruptible and imperfect. Everything beyond the moon was perfect, eternal, and unchanging. Newton shattered this paradigm. He unified heaven and earth and showed that the same laws of physics describe both. About 20 years after his insight with the inverse square law, Newton took a break from his interest in alchemy and biblical chronology and revisited the question of motion due to gravity. He'd been provoked by his colleagues and rivals at the Royal Society of London. They challenged him to solve a much harder problem than any he'd previously considered and that none of them knew how to solve. If there, if there was a force of attraction emanating from the sun that weakened according to an inverse square law, how would the planets move in ellipses? Newton is said to have replied at once when he when his friend Edmund Halley posed, posed the question, but asked a flabbergasted Halley, "What? How do you know?" "Why, I have calculated it," said Newton. When Halley asked him to explain his reasoning, Newton set about reconstructing his artwork in the various torrent of activity, a creative outpouring almost as frenzied as what he had done as a student during Planck's years. Newton wrote the Principia by assuming his laws of motion and gravity as axioms and using his calculus as a deductive instrument. Newton proved that all three of Kepler's laws fall as logical necessities. The same was true for Galileo's law of inertia, the isochronism of pendulums, the odd number rule for balls rolling down ramps, and the parabolic arcs of projectiles. Each of them was a corollary of the inverse square law and F equals ma. This appeal to deductive reasoning shocked Newton's college and disturbed them on philosophical grounds. Many of them were empiricists. They thought that logic applied only within mathematics itself. Nature had to be studied by experiment and observation. They were dumbfounded by the thought that nature had an inner mathematical core and that phenomena in nature could be deduced by logic from empirical axioms like the laws of gravity and motion. The two-body problem. The question that Halley posed to Newton was monstrously difficult. It required the conversion of local information into global information, the central difficulty of integral calculus and prediction that we discussed in Chapter 7. Think about what would be involved in predicting the gravitational interplay of two bodies. To simplify the problem, pretend that one of them, the Sun, is infinitely massive and hence motionless, while the other planet in orbit moves around it. Initially, the planet is at some distance from the Sun at a given location and moving with a given speed in a given direction. In the next instant, the planet's velocity carries it to its next location, an infinitesimal distance from where it was a moment ago. Since it's now at a slightly different places, it feels di- a slightly different place. It feels a slightly different gravitational pull from the sun, different in both direction and magnitude. The new force, computable from the inverse square law, tugs the planet again and changes its speed and its direction of travel by another infinitesimal amount, computable from f equals ma during the next infinitesimal increment of time. The process continues ad infinitum. All these infinitesimal local steps have to be integrated somehow, added together to produce the whole orbit of the moving planet. Integrating f equals ma for the two-body problem is thus an exercise in the use of the infinity principle. Archimedes and others had applied the infinity principle to the mystery of curves, but Newton was the first to apply it to mystery of motion. As hopeless as the two-body problem seemed, Newton managed to solve it with the help of the fundamental theorem of calculus instead, instead of inching the planet forward instant by instant in his mind. He used calculus to thrust it forward by leaps and bounds, as if by magic. His formulas could predict where the planet would be as well as how fast it would be moving as far as far into the future as he desired. The infinity principle and the fundamental theorem of calculus entered Newton's work in another novel respect. In his first attack on the two-body problem, he had idealized the planet and the sun as point-like particles. Could he model them more realistically as the colossal spherical balls that they actually were and still solve the problem? And if he could, would his result change? This was another extraordinarily difficult calculation at that time in the development of calculus. Consider what would be needed to tally up the nectar of the giant sphere of the sun and smaller on the smaller but still giant sphere of the earth. Every atom in the sun pulls on every atom in the earth. The difficulty is that all those atoms are at different distances from one another. The atoms at the back of the sun are farther away and hence exert a weaker gravitational pull on the atoms on the earth than the atoms in the front of the sun. Moreover, the atoms on the left and right sides of the sun pull the earth in conflicting directions and with varying strengths depending on their own distances from the earth. All of these effects have to be added up, putting the pieces back together again for this problem was harder than anything one had ever done in integral calculus. When we solve it today, we use a method called triple integration. It's a beer. Newton managed to solve this triple integral and found something so beautiful and so simple. It is almost unbelievable even today. He found that he could get away from the pretending that all the mass of the spherical sun was concentrated at its center. Likewise, for the Earth, his calculations showed that the orbit of the Earth would be the same either way. In other words, he could replace the giant spheres with infinitesimal points without incurring any error. How's that for a lie that how's that for a lie that reveals the truth? There were many other approximations in Newton's calculus, however, whose effects were more serious and problematic. For the sake of simplicity, he completely ignored the gravitational pulse exerted by all the other planets. Plus, he continued to assume that gravity acted instantaneously. He knew that both of these approximations couldn't possibly be correct, but he didn't see any way to make progress without them. He also confessed that he had no explanation for what gravity actually was or why it obeyed the mathematical description he'd given it. He knew that his critics would be suspicious of his whole program to make his work as convincing and persuasive as possible, he quotes it in the reassuring language of geometry, the gold standard of rigor and certainty as understood at the time. But it was not traditional Euclidean geometry, it was a peculiar, idiosyncratic mixture of classical geometry and calculus. It was calculus in geometric clothing. Nonetheless, he did his best to give it a classical veneer. The style of the Principia is old school Euclidean, following the format of classical geometry. Newton started from axioms and postulates, his laws of motion and gravity, and treated him as crescent foundation stones. On them he built an edifice of lemmas, proportions, theorems, and proofs, and all deduced by logic. One from the other is an unbroken chain reaching all the way back to the axioms. Just as Euclid gave the world his immortal 13 books of the elements, Newton gave of the world 3 books of his own. Without false modesty, he called the third one the system of worlds. His system depict his system de, de, depicted nature as a mechanism. In the years to come, it would often be compared to a clockwork. It jigs spinning, its springs stretching, all its parts moving in sequence, a wonder of cause and effect, applying the fundamental theorem of calculus and armed with power series. Ingenuity and luck, Newton could often solve his differential equations exactly. Instead of grabbing forward instant by instant, he could leap ahead and forecast the state of his clockwork indefinitely far into the future, just as he'd done from the two-body problem of a planet orbiting the sun. In the centuries after Newton, his system was refined by many other mathematicians, physicists, and astronomers. It was so trusted that when the motion of a planet disagreed with its predictions, astronomers assumed they were missing something important. This was how the planet Neptune was discovered in 1846. Irregularities in the orbit of Uranus suggested the presence of unknown planet beyond it, an unseen neighbor that was perturbing Uranus gravitationally. Calculus predicted where the missing planet should be, and when astronomers looked, there it was. Newton meets hidden features. By the mid-20th century, it seemed that physics had finally the, on the, move on from Newtonian mechanics. Quantum theory and relativity had put the old workhouse out to pasture. Yet even then it enjoyed one last hurrah that, thanks to the space race between the United States and Soviet Union. In the early 1960s, Katherine Johnson, the African-American mathematician and heroine of Hidden Features, used the two-body problem to bring astronaut John Glenn, the first American to orbit the Earth, safely back home. Johnson's broke new ground is in so many ways. In her analysis, the two gravitating bodies were a spacecraft and the Earth, not a planet, and the Sun as they had been for Newton. She used calculus to predict the position of the moving spacecraft as it orbited the Earth, rotating underneath it, and to calculate its trajectory for successful re-entry into the atmosphere. To do that, she needed to include complications that Newton had left out, the most vital of which was that the Earth is not perfectly spherical, it bulges slightly at the equator and flattens at the poles. Getting the details right was a matter of life and death. The space capsule had to enter the atmosphere at the right angle or it would burn up. and it had to land at the right spot in the ocean. If it's placed down too far away from the rendezvous site, Glenn might drown in his space capsule before anyone could reach him. On February 20, 1962, Colonel John Glenn completed 3 orbits of our planet, and then, guided by Johnson's calculations, he re-entered the atmosphere and landed safely in the North Atlantic Ocean. He was a national hero. Later, years later, he would be elected as U.S. Senator. A few people were aware that on the day he made history, he had refused to fly his mission until Katherine Johnson herself had checked all the all the last-minute calculations for it. He trusted her with his life. Katherine Johnson was a computer for for national for National Aeronautics and Space Administration at a time when computers were women, not machines. She was there near the start, when she helped Alan Shepard become the first American in space, and she was there near the end when she worked on the trajectory for the first moon landing. For decades, her work was unknown to the public. Thankfully, her pioneering contributions and her inspiring life story have now been recognized. In 2015, at age 97, she received the Presidential Medal of Freedom from President Barack Obama. A year later, NASA named a building her a building after her. At the dedication ceremony, the NASA official reminded the audience that millions of people around the world watched Alan Shepard's flight, but what they did not know at the time was that the calculations that got him into space and safely home were done by today's guest of honor, Katherine Johnson. Calculus and Enlightenment. Newton's picture of a world ruled by mathematics reverberated far beyond science. In humanities, it served as a foil for romantic poets like William Blake, John Keats, and William Wordsworth. At a raucous dinner party in 1870, Wordsworth and Keats, among others, agreed that Newton has destroyed the poetry of the rainbow by reducing to its prismatic colors. They raised their glasses in a boisterous toast. Newton's head and confusion to mathematics. Newton got a warmer reception in philosophy, where his ideas, influenced by Voltaire, David Hume, John Locke, and other Enlightenment thinkers, they were taken with the ardor of with the power of reason and the explanatory successes of his system, with its clockwork universe driven by causality. His empirical deductive approach, anchored in facts and fueled by calculus, swept away the a priori metaphysics and early philosophers. I'm looking at you, Aristotle. Beyond science, it left its mark on Enlightenment conceptions of everything, from determinism and liberty to natural law and human rights. Consider, for example, Newton's way over Thomas Jefferson, architect, inventor, farmer, third president of the United States, and author of the Declaration of Independence. There are there are echoes of Newton throughout the Declaration. Right from the start, the phrase, the phrase "we hold these truths to be self-evident" announces the rhetoric structure, as Euclid did in the Elements, as Newton did in the Principia. Newton Jefferson began with the axioms, the self-evident truths of his subject. Then, by force of logic, he deduced a series in inescapable proportions for those axioms, foremost important of which was that the colonists had the right to sever themselves from British rule. The declaration justifies that separation by appealing to the laws of nature and of the nature's God. Incidentally, notice the post-Newtonian deism implicit in Jefferson's ordering. God comes after the law of nature and only in subordinate role the nature's God. The argument is clinched by the causes which impel the colonists to the separation from the British crown. Those causes by the those causes play the role of Newtonian forces impelling the clockwork motion determining the effects that must follow, in this case the American Revolution. If all of this seems far-fetched, keep in mind that Jefferson referred Newton in a macabre act of devotion. He acquired a copy of Newton's death marks, and after he was no longer president, Jefferson wrote to his old friend John Adams on January 21, 1812, about the pleasure of leaving politics behind. I have given up the newspaper in exchange for Tacitus and Thucydides, for Newton and Euclid, and I find myself much happier. Jefferson's fascination with Newtonian principles carried over to his interest in agriculture. He wondered about the best shape for the moldboard of a plow. A moldboard is the curved part of a plow that lifts and turns the soil cut by the plowshare. Jefferson framed the question as one of efficiency. How should the moldboard be curved so that it would encounter the least resistance to the rising sod? The surface of the moldboard needed to be horizontal in front so that it could get under the cut soil to lift it, and it should then gradually curve to become perpendicular to the ground toward the back so that it could turn the soil and push it aside. Jefferson asked a mathematical friend to address this optimization problem in many ways. The question was reminiscent of one that Newton himself had posed in the Principia on the shape of a solid body of least resistance to motion through water. Guided by that theory, Jefferson had a plow fitted with a wooden moldboard of his own design. He reported in 1798 an experiment that an experience of 5 years had enabled me to say it answers in practice to what it promises in theory. It was Newtonian calculus in the service of farming, from discrete to continuous systems. For most part, Newton had applied calculus to one or two bodies at most: a swinging pendulum, a flying cannonball, a planet cycling the sun. Solving differential equations for three or more bodies was a nightmare, as he'd learned the hard way. The problem of a mutual gravitating sun, Earth, and Moon had already given him a migraine. So analyzing the whole solar system was out of the question, far beyond what even Newton could do with calculus. As he put it in one of his unpublished papers, unless I am much mistaken, it would exceed the force of human wit to consider so many causes of motion at the same time. But surprisingly, going even higher, all the way up to infinitely many particles, made differential equations tractable again, as long as those particles form a continuous medium, not a discrete set. Recall the difference. A discrete set of particles is like a collection of marbles and spread out on the floor. It's discrete in the sense that you could touch one marble, move your finger through empty space, touch another one, and so on. There are gaps between the marbles. In contrast with a continuous medium like, for instance, a guitar string, you would never have to lift your finger from the string as you trace along its length. all the particles in the guitar string hang together. Not really, of course, because a guitar string, like all other material objects, is discrete and granular at atomic scale. But in our minds, a guitar string is more aptly regarded as a continuum. This useful fiction frees us from the core of having to contemplate trillions and trillions of particles. It was by addressing the mysteries of how continuous media move and change, how guitar strings vibrate to make such warm music, or how heat flows from warm spots to cold spots, that calculus made its next great strides toward changing the world. But first, calculus had to change itself. It needed to enlarge its concept of what differential equations were, and what they could describe. Ordinary versus differential equation. When Isaac Newton explained the elliptical orbits of the planets, and when Katherine Johnson calculated the trajectory of John Glenn's space capsule, they were both solving a class of differential equations known as ordinary differential equations. The word ordinary is not meant to be pejorative. It's the term of art for differential equations that depend on just one independent variable. For example, in Newton's equation for the two-body problem, the position of a planet was a function of time. It kept changing its location from moment to moment according to the text or dictates of F equals ma. That ordinary differential equation determined how much the planet position would change during the next infinitesimal increment of time. In this example, the planet's position is the dependent variable since it depends on time, the independent variable. Likewise, time was the independent variable in Alan Parelson's model of HIV dynamics. He was modeling how the concentration of virus particles in the blood decreased after administration of an antiretroviral drug. The issue again was changes in time, how the viral concentration changed from moment to moment. Here, concentration played the role of the dependent variable. The independent variable was still same. More generally, an ordinary differential equation describes how something, the position of a planet, the concentration of a virus, changes infinitesimally as the result of an infinitesimal change in some else, such as an infinitesimal increment of time. What makes such an equation ordinary is that there is exactly one something else, one independent variable. Curiously, it does not matter how many dependent variables there are. As long as there is only one independent variable, the differential equation is considered ordinary. For example, it takes three numbers to pinpoint the position of a spacecraft moving in three-dimensional space. Call those numbers x, y, and z. They indicate where the spacecraft is at a given time by locating it left or right, up and down, front or back, and thus telling us how far away it is from some arbitrary reference point called the origin. As the spacecraft moves, it, its XYZ coordinates change from moment to moment, thus their functions of time. To emphasize their time dependence, we could write them as xt, yt, zt. Ordinary differential equations are perfectly tailored to discrete systems consisting of one or more bodies. They can describe the motion of a single spaceship entering the atmosphere, a single pendulum swinging back and forth, or a single planet as it orbits the sun. The catch is the catch is that we need to idealize each of the individual bodies as a point-like object, an infinitesimal speck with no spatial extent. Doing that, doing that allows us to think of it as existing at a point with coordinates xyz. The same approach the same approach works if there are many point-like particles, a swarm of tiny spaceships, a chain of pendulums connected by springs, a solar system of 8 or 9 planets, and countless asteroids. All these systems are described by ordinary differential equations. In the centuries after Newton, mathematicians and physicists developed many ingenious techniques for solving ordinary differential equations and thus forecasting the future of the real-world systems they describe. The mathematical techniques involved extensions of Newton's ideas about power series, Leibniz's ideas about differentials, clever transformations that could allow the fundamental theorem of calculus to be invoked, and so on. This was an enormous industry, and it continues to this day. But not all systems are discrete, or at least not all of them are best viewed that way, as we saw with the example of a guitar string. Consequently, not all systems can be described by ordinary differential equations. To understand why not, let's have another look at our imaginary bowl of a soup cooling off on the kitchen table. A bowl of soup is, at one level, a discrete collection of molecules all bouncing around erratically. Yet there's no hope of seeing them, measuring them, or quantifying their motion, so nobody would ever think of using ordinary differential equations to model the cooling of a bowl soup. There are simply too many particles to deal with, and their motion is too irregular, haphazard, and unknowable. A much more practical way to describe what's happening is to think of the soup as a continuum. This is not really true, but it's useful. In a continuum approximation, we pretend that the soup exists at every point inside the three-dimensional volume of the bowl soup. The temperature T at a given point xyz depends on time t. All of this information is captured by function t xyz t. As we will see shortly, there are differential equations for describing how these functions changes in space and time. Such a differential equation is not an ordinary differential equation. It can be because it doesn't depend on just one dependent variable. In fact, it depends on four of them, x, y, z, and t. It's a new kind of beast, a partial differential equation, so called because each of its independent variables plays its own part in causing change to occur. Partial differential equations are much richer than ordinary differential equations. They describe continuous systems moving and changing in space and time simultaneously, or in two or more dimensions of space. Along with a cooling bowl of soup, the saggy shape of a hammock is described by such an equation. So is the spreading of a pollutant in a lake of flow of air over the wing of a fighter plane. Partial differential equations are extremely difficult to handle. They make ordinary differential equations, which are already difficult, seem like child's play. Yet they are also extremely important. Our lives depend on them whenever we take to skies. Partial differential equations and the Boeing 787. Modern airplane flight is a wonder of calculus, but it was not always so. In a simpler time, at the dawn of aviation, the first flying machines were invented by analogy with birds and kites, by engineering savvy, and by persistent trial and error. The Wright brothers, for example, used their knowledge of bicycles to devise their three-axis system for controlling airplanes in flight and overcoming the inherent instabilities. As aircraft become increasingly so sophisticated, however, it became necessary to use more sophisticated means to design them. Wind tunnels allowed engineers to test the aerodynamic properties of their flying machines without the craft leaving the ground. Scale models, in which the designer built in tiny mock-ups of the real planes, allowed aerotics to be tested without building costly full-size models. After World War II, aeronautical engineers added computers to their design arsenal. The vacuum tube behemoths that had been used for the code-breaking, artillery calculations and weather forecasting were deployed to help create modern jet aircraft. Computers could be used to solve the complex partial differential equations that inevitably arose in the design process. The math involved could be horrendously difficult for several reasons. For one, for one thing, the geometry of an airplane is complicated. It's most like a sphere or a kite or a balsa wood glider. It's much more complex shape with wings, fuselage, engineers, tails, flaps, and landing gears. Each of these deflects the air rushing past at the plane at high speed, and whenever onrushing air is deflected, it exerts a force of whatever deflected it, as anyone who has ever stuck his or her hand out of window of a car speeding down the highway knows. If an airplane if an airplane wings is shaped properly, the unrushing air tends to leave it. If the plane is moving fast enough down the runway, this upward force lifts the plane off the ground and keeps it aloft. But whereas lift is a force perpendicular to the direction of oncoming inflow, another kind of force, drag, acts in a direction parallel to the flow. Drag is like friction. It resists the plane motion and slows it down, causing its engines to work harder and burn more fuel. Calculating the size of this lift and drag force is a brutally difficult calculus problem, far beyond the ability of any human being to solve for a realistically shaped airplane. Yet, such problems must be solved. They are crucial to airplanes design. Consider the Boeing 787 Dreamliner. In 2011, Boeing, the world's largest aerospace company, rolled out its next generation mid-sized jet for transporting 200 to 300 people on long-haul flights. The flight was touted as 60% quieter and 20% more fuel efficient than Boeing 767, which it was designed to replace. One of its most innovative features was its use of carbon fiber reinforced polymers in the fuselage and wings. The space-age composite materials are lighter and stronger than aluminum, steel, and titanium, the conventional materials of choice for jet aircraft. Because they're lighter than metals, they save fuel and also make it easier for the plane to fly faster. But, per, but perhaps the most innovative thing about the Boeing 787 was the mathematical and computational foresight that went to it, that in the design of any other previous plane, calculus and computers saved Boeing as enormous amount of time. Simulating a new prototype is a lot faster than building it. They also save Boeing money computer simulations are much cheaper to run than wind tunnel tests, the price of which has skyrocketed in the past few decades. Douglas Ball, the chief engineer of enabling technology and research at Boeing, pointed out in an interview that during the design process for the Boeing 767 in the 1680s, the company built and tested 77 prototype wings. 20 years later, by using supercomputers to simulate the Boeing 787 wings, they had to build and test only 7 of them. Partial differential equations entered into the process in myriad ways. For example, along with the calculations of lift and drag, Boeing's applied mathematicians uh, ma- Boeing's applied mathematicians use calculus to anticipate how the airplane's wings would flex when moving at 600 miles per hour. When a wing is subjected to lift, the lift force causes the wing to flex and to flex outward and twist. One phenomenon engineers want to avoid is a dangerous effect called aeroelastic flutter, an deviation of of the fluttering Venetian blinds when a breeze blows past them. In the best case, such unwanted vibrations of the wings produce a bumpy, unpleasant ride. In the worst case, the oscillations create a positive feedback loop. As the wings flutter, they alter the airflow over them in a way that makes them flutter even more. Aeroelastic flutter has been known to damage the wings of test aircraft and to cause structural failures and crashes, as occurred once with Lockheed F-117 Nighthawk stealth fighter during an air show. If a severe flutter occurred on a commercial flight, it put hundreds of passengers at risk. The questions that govern aeroelastic flutter are closely related to those we mentioned earlier in our discussion of facial surgery. There, the modelers channeled the spirit of Archimedes when they approximated a patient's soft tissue as skull using hundreds of thousands of gem-shaped polyhedrons and polygons. In the same spirit, Boeing's mathematicians approximated a wing with hundreds of thousands of tiny cubes, prisms, and tetrahedrons. The simpler shapes played the role of elemental building blocks. Stiffness and elastic properties were assigned to each of them, just as in the facial surgery modeling, and then the building blocks were subjected to the relevant pressures and pulls imparted by their neighbors. The partial differential equations of elasticity theory predicted how each simple element would respond to those forces. Finally, with the help of supercomputer, all those responses were combined and used to predict the overall vibration of the wing. Similarly, partial differential equations were used to optimize the combustion process in the aircraft engines. This is an especially complicated problem to model. It involves the interplay of three different branches of science. Chemistry, the field undergoes hundreds of chemical reactions at high temperature. Heat flow, the heat redistributes itself within the engine as chemical energy is converted into mechanical energy, spinning the turbine blades. And fluid flow, how hot gases swirl in the combustion chamber, and predicting their behavior is an exceedingly difficult problem in light of the turbulence of such gases. As before, the Boeing team used an Archimedean approach. They cut the problem into pieces, solved the problem for each piece, and put the pieces together again. its infinity principle in action, the divide and conquer strategy in which all of calculus rests. Here it was aided by supercomputers and a numerical method known as finite element analysis. But at the heart of it all is still calculus embodied in differential equations. Ubiquity of partial differential equations. The application of calculus to modern science is largely is, is largely an exercise in the formulation, solution, and interpolation of partial differential equations. Maxwell's equation for electricity and magnetism are partial differential equations. So are the laws of elasticity, acoustics, heat flow, fluid flow, and gas dynamics. The list goes on. The black, the black skulls The black source the black source model for pricing financial options, the Hawking-Hartley model for the speed of electrical impulses along never fibers, partial differential equation all. Even at the cutting edge of modern physics, partial differential equations still provide the mathematical infrastructure. Consider Einstein's general theory of relativity. It reimagines gravity as a manifestation of curvature in the four-dimensional fabric of space-time. The standard metaphor invites us to picture space-time as a stretchy, deformable fabric like the surface of a trampoline. Normally, the fabric is pulled out, but it can curve under the weight of something heavy placed on it, say a massive bowling ball sitting at its center. In much the same way, a massive celestial body like the Sun can curve the fabric of space around it. Now imagine something much smaller, say a tiny marble, which represents a planet rolling the trampoline's curved surface. Because the surface sucks under the bowling ball's weight, it deflects the marble's trajectory. Instead of traveling in straight line, the marble follows the contours of the curved surface and orbits around the bowling ball repeatedly. That, says Einstein, is why the planets go around the sun. They are not feeling a force. They are just following the path of least resistance in the curved fabric of space-time. As mind-boggling as this theory is, at its mathematical core are partial differential equations. The same is true of quantum mechanics, the theory of the microscopic realms. In its governing equation, the Schrödinger equation is a partial differential equation too. The next chapter take a closer look at such equations to give you a feel for what they are, when they came from, and why they matter in our everyday lives. As we'll see, partial differential equations do more than describe the bowl of soup cooling off on the kitchen table. They also explain how the microwave nuke it.